Okay, I think I'll start. All right. So start recording. Good. Share my screen. Yeah, I'm going to start the lecture and take any questions you may have on the assignment on CTL Model Checker maybe towards the end of the lecture. So if you have any questions, hold your questions till the end. So as I had mentioned in the mail that I sent you about the agenda for today, I'm going to be, see, so far you've seen how to use BDDs to to represent formulas and manipulate formulas which characterize sets of states towards computing fixed points, which is what pretty much model checking is about. At least CTL model checking can be viewed as a repeated computation of fixed points. So starting today, I'm going to be yes, I will show you. I mean, of course, we introduced SAT solvers before BDDs. So how SAT solvers can be used. And as you in doing the same thing, general model checking, and what the pitfalls there are, and what are the dominant methods in which SAT solvers are used for doing model checking. So of course, you could do the same thing that you did, as you saw in the CTL model checking. The most intensive or compute intensive part of the computation that goes in doing model checking is the existential elimination. Okay, that is embedded inside computing the set of states satisfying AX and EX. All the rest of the operators are done using repeated applications of that thing. So the formula that you end up getting will have, if you were to not be eliminating the existential quantifiers, is a formula with nested quantifiers. Okay, and when you're doing with BDD, you eliminate those that quantifiers as an operation as you go along in each step of the fixed point computation. Now, you could do the same thing here as well. And that's what I'm showing here. Okay, so this is for doing just this is an algorithm for accumulating all the reachable states, starting from the initial set of states, okay, which is what you do when you do a forward fixed point computation. Okay, so that is what I've illustrated this for, and I mean you can see how this idea can be used in other places as well. So start with an initial state, and this is the transition relation. Instead of using BDDs, we'll just assume that the transition relation is expressed as a formula, maybe CNF, because SAT solvers use CNF. Eventually they'll have to be converted into CNF. That's the form in which they manipulate. Yeah, for some of you who, I don't know, I mean, I have not gone through this. I'm not going to I encourage you to listen to the lectures on SAT solvers that I have covered in the SMT class, which I have uploaded to the model checking Moodle page as well. So there I talked about something called Cyton encoding, where you don't have to reduce all operators, Boolean connectives, to, I mean, there is a way to convert them into CNF without actually encountering the obvious blow up that you get. Okay, so that's a matter of detail. So, but the assumption is that rather than computing the fixed point, you will just keep it in some CNF normal form there. And then this, suppose this is the property that you want to verify, which is also a formula in terms of the variables that are shown here. So you start this loop, which is pretty much similar to the fixed point computation loop. So you start by checking if the, this is, as I said, this is for checking an invariant property, that if something like an AG of P, okay, G of P, that P is invariantly true on all things. And as you saw right in the beginning, before we got into CTL model checking, etc., that could be done by just accumulating all the reachable states. And that's what I'm showing you here, okay? So if the initial state, if one of the initial state itself violates the property, then you can declare failure and quit. And that's what is done here. for which you may take the conjunction of phi c, okay, which is initialized to init, and the negation of prop, and then do a SAT check. If that is true, that means that one of the initial states is violating the property. Then you say property failed. If not, you have to compute the image of the current accumulated set of states over the current accumulated states using phi t, and this is the this is the image. So what you will have to do is, in SAT solvers, they so they usually don't take they only work on propositional logic, quantifier-free propositional logic. You can eliminate this quantifier by just plugging in zeros and ones for these things and taking the disjunction. Of course, that can have an explosion in the size of the CNF, but I'm saying in principle you can do that. I'm not saying that this is what you should do, but just as a theoretical concept. I mean, you could eliminate that. Then you do the renaming, to be able to prepare it for thing, and then you check if you've reached the fixed point. I mean, if the new image that you construct, that you compute, is no, what am I saying? Yeah. So if it is already in the here you check if you've reached the fixed point or not. Okay, if you've reached the fixed point, if the image is already included in phi c, which is, once again, if this is valid. Okay, how do you check validity using SAT solvers? You take the negation of this and then check if it is unsat, which can be done. Then you declare the property is verified. Otherwise you add the newly computed image to the thing. That is, you take the disjunction of the current accumulated set of reachable states, and then you repeat. Okay. So basically, the point is, although I've illustrated for doing the forward fixed point computation, on image computation, you can see that whatever that you've done for CTL model checking, you can do as long as you take care of the existential quantification explicitly by plugging in the different combinations of the valuations for x1 to xn. So that's a naive way of doing it. Okay, so in principle you can do this. Okay, and then you can use a SAT solver also, as SAT solver to do it. But what are obviously there are problems. We've already talked about this. So constructing the phi image and its conversion to CNF can have an exponential blow up in the number of clauses. Even when you use that encoding that I talked about in the SAT lecture, in general, the existential quantification elimination will have in some CNF or pseudo CNF form is bound to have an explosion. Okay, so this kind of doing it is not practical for doing in SAT solving. It does not scale in practice, and therefore what is done is, if you were to use existential quantification elimination in computing the fixed point, you're better off using BDDs, because the BDDs construct it in a canonical representation, and there, as long as your intermediate Boolean functions that you generate are compactly representable in BDDs, the existential quantification elimination itself is not that big. And because CNF can have explosion, that's the reason for this method not being practical when you are employing SAT. Okay. So is that, yeah. So any questions there? So is that the points that I made seems reasonable and clear? Okay. So what is the method that is used? Okay. Now there are several methods. Okay. So when SAT solvers, here is the history. Okay. A little bit of history. So model checking, the BDDs got introduced in around 1975, 1980. That was when it was kind of invented, or at least all these operations and constructing things and tools to manipulate BDDs, etc. Yeah, so they were invented in the mid to late 70s. Okay, so after that there was this, so then model checking itself, early 1980s, 1985, and then there was this BDD, symbolic model checking, which used BDD, and that was the state of the art at that time. And SAT solvers, they started becoming extremely competitive only after several breakthroughs that happened in the late 90s and early 2000. Okay, so and they continue to improve in their scalability to real problems, and therefore, so people started looking at if SAT solvers could be used, and you see that's why, yeah, and they still found that existential quantification elimination was a problem, and therefore there were alternative approaches that that people started thinking about as how you could use a SAT solver in model checking. And one of the ideas that came up was this bounded model checking, which basically says that, okay, can I still use it? Okay, I mean, you will have to compute fixed points eventually if you want to ensure that you have accumulated all the states on which, or the paths on which you need to check your formula, and certainly for general temporal logic model checking. But is there a way to do that without in an incomplete way? Okay, and that is how it started. Okay, and you focus on counterexample generation. Okay, model checking once and for all proves that a property is conclusively true for a given model, but in practice, what is even an incomplete method that focuses on counterexample generation, especially that can guarantee that counterexamples up to a given bound on the length of the counterexample, if you could guarantee that even if it is incomplete, it is usable. Okay, in practice, and an engineering team, they really, in any case, they use effective methods for eliminating bugs. So even in incomplete form, and you will see that why this method is incomplete. That's how it started. And then there were several methods that came about to make this kind of model checking complete, okay, without actually doing in every step the existential quantification elimination. So that is the kind of the chronology of the thing. So we will first see what bounded model checking is and how it uses SAT solvers in an effective way. Okay? Okay, these things are there. Okay, these things you all know. Yeah, so unwinding a transition system. So this is something that you've already seen. So yeah, if you want to check a property of the form G of P, where P is a predicate, okay? That's why I call this, I'm illustrating this for invariant properties, okay? That you want to show that a predicate on a state is invariantly true on all paths. Then if you check this, you start from the initial state and you construct this formula, okay? What does the formula on the left side here represent? It represents a path of length. T is the transition relation, S naught is the initial predicate. And here I am, this is a conjunction of T's over S naught to SK, okay? So this denotes a path of length K in the Kripke model. And if you want to check that, if you want to check P, what you want to do is you want to check that not P, if not P is violated. So bounded model checking, as I said, the idea there is to check if counterexamples of up to a certain length exist or not. Okay, so if you then want to check that if P is violated in any one of the states along the K length path, then you can add this disjunction of not P on each of these states that appear in the path, and then check if it is satisfiable. If there is a satisfying instance, if one exists, then you've found a counterexample of length of K, of length K. It's I plus 1 here, so because you've iterated over K. So if it's unsat, then what can you conclude? Then you can conclude, because if it is unsat, then you know that this is the negation of this is valid. Therefore, you can conclude that for all paths of length up to K, that this is safe, that P is not violated. Okay. Now you could do this in an incremental way for increasing lengths, so maybe you will do it up to some bound. So that is the idea behind bounded model checking. Okay. So for safety properties of this kind, G of P, so what you do is, this is exactly what you verify. This is what I had shown in the previous slide. So in order to check this, if you want to check that the counterexamples to G of P of length K or less don't exist, then you will have to check the satisfiability of this formula, and then you can do this. Of course, this one is not in CNF, but I'm assuming that you generate this formula and then ship it off to SATSOM. So now do you understand? So the idea behind bounded model checking, key takeaway is that it checks for existence of counterexamples to a given property of bounded up to a bounded length, and it does that by generating a formula whose satisfiability represents the existence, gives you the existence of a counterexample of length K or less. Okay, so that is the idea. So is it clear about why this, if this is SAT, that there is a counterexample of length less than or equal to K? If you still have doubt, you will have to ask a question here. Okay. So you could do a similar thing. Okay. So I'm illustrating it for a simple invariant property. How about liveness property? Okay. So as you can see, for safety properties, the counter example is of bounded, I mean, you have finite counter example, whereas for liveness property, let's suppose that you want to check for f of p, that you want to check if there is violation to something eventually, some predicate eventually holds. For that, you cannot just do with, okay, so there you rely on the fact that every counter example has, is of a lasso shape for finite state systems. So if there is a counter example to FP, then it has to be of shaped like this, okay, with a tail and a part that loops back into some state. So, you can now generate, okay, you can now generate, check if there are longer and longer counterexamples, lasso-shaped counterexamples of longer and longer length, where the length of a lasso I define as this path from S0 to SK before it lassos back. Okay? Now you could generate a formula that whose satisfiability shows that there is a witness, satisfying instance becomes a witness to the existence of such a counterexample. So you remember that the counterexample for a liveness property like FP is one where not P continuously holds, and it hits a loop like this. Then you know that this one is an infinite counterexample. So this can also be converted into a formula on which SAT can be checked. So the first part here from IS0 to SK says the existence of that there is a path, okay, as per the transition relation, that's K long. And this part here, the second part, this disjunction, the big wedge here, says that one of these things, one of the states, SK is equal to, it loops back into one of the states, okay? So for any given L, okay? So, that there is from 0 to K, it can loop back to any one of these states from S0 to SK. So that can be checked as a equality, okay, over between this SK. Yes, that SK plus 1, that is this transition from SK, the transition, the state that is the successor to SK, that's what SK plus 1 denotes. If that is equal to S plus 1. So here, SK plus 1 is the successor to SK, and I'm checking if this part checks if it is lassoed, okay? Now, if you can find such a K wherein every state from S0 to SK not P is true and it is lassoed, then, and that's what the not P is checked here in the last part, and it has lassoed, which is checked, then you have found a counterexample of length K. And then if you want to, then you can use SAT to, you can incrementally increase K to check if there are longer and longer counter examples. Okay, so that is what the idea of bounded model checking is. So you see, to think here, you are eliminating the this job of having to use existential quantification elimination, but there is no magic here. I mean, you're using you're trading that thing off with constructing bigger and bigger formula. So every time that you will have to do, check, longer counterexample, you have to construct a formula that is longer in terms of the number of clauses it has. Now, so you may ask, what is it that you're gaining? I mean, aren't you increasing this length size? But of course, here, each time it is eliminating number of different counterexamples. For each k, it is eliminating a number of different counterexamples of that length. For linear each time, for linear, every time you're adding only one copy of of t. Okay, there are two reasons why, despite this works out better than existential qualification elimination for two reasons. See, SAT solvers have become very efficient in solving, checking satisfiability of formulas that have millions or even tens of millions of variables and millions of clauses. So the size is really not as much of an issue. So you could use this method for for fairly big values of k. So you could do that for, resulting in checking, eliminating fairly deeply embedded bugs. Okay, because each time, if you prove that this is unsat, you have guaranteed that there is no counterexample of a certain up to a certain length. Okay, this reminds me of a question that Diganta, I think you asked when we were discussing these BDDs and model checkers. You asked that question: if it gives some partial results, if it croaks, if it just runs out of steam, if it even gives some partial results about, oh, I have explored the design for up to a certain depth and so on. Bingo! This is one way to do that. Okay, and I mean, I guess even in model checking you can do that, but then that how many iterations you have done using that approach as well. But here, that is the primary idea. Another reason why this is very practical, is quite efficient, is that you see you're using each time you're doing. Of course, each time when you increase the k, you have to invoke a SAT call. Okay, again, but there is something called when you've checked something for a certain formula and you're adding something to it, more constraints, SAT solvers work very efficiently. There is something called incremental SAT solving. If you've already checked that there are no counterexamples for up to length k, to check for absence of counterexample of length k plus 1, all you're doing is you're adding one copy of t here, some more of this check, and a little bit of that check. So SAT solvers, so you can reuse a lot of the effort, such as conflict clauses, etc., that are effort that is effort expended in checking for k, in checking absence of counterexamples of length k, which is a SAT, in checking for one more unwinding of this transition. And there is that thing called incrementals. As long as you are only adding something and adding more constraints, you can exploit that. And these two features of SAT solvers make this approach very effective. Okay, any questions here? So there's several points I made, and I want to make sure that you have understood the key ideas behind model checking and why this is pretty very effective in practice. Okay, even though it is an incomplete procedure. Okay, it only guarantees absence of counterexamples for up to a certain length, but not in the way that I've shown till now, that it does not do guarantee that this property is proven for the transition system. Any questions?
Converting this into something very complete is going to be difficult, right?
No. I will get to that. Okay, so that is where all the I would say that some of them are no longer research ideas. Even to this day, there's a lot of research going on, but some of the so that is, yeah, I will get to that. What are some of the ways that have been done since? So as I said, this was introduced in early, late 1990, like you said, 1999 in that paper, in 2001. So the next 10 years saw several developments in how to make this technique complete. Okay, and we will discuss a few of those things. One very effective ones that was introduced was inductive model checking. Okay, and two methods in that have become very effective. Okay, and we will look at those things, and to the point that one of those methods, which is called property directed reachability, or sometimes it is called IC3, is very effective in practice, and it is part of a lot of model checkers that are used by industries. Okay? So we will see how those things are done, how things are done. So that was the research between 2001 and 2010. Several of those techniques are fairly mature now, and what I'm going to be discussing, introducing, covering in this class are a couple of techniques that are fairly mature, that are used in practice. Okay. Now, if your question is if it can solve millions of lines of code, software, obviously not. Okay, but they can do successfully solve fairly pretty big systems in hardware, and these techniques have been more successful in hardware than in software, but now I would say that even in software, some of those completion techniques are becoming popular even in practice. Any other questions? So key thing here is to understand how you are getting around this not doing existential quantification elimination. Okay, that is the key takeaway that you will have to understand. If you have doubts about that, you better yell and scream right now. Okay. Okay. Of course, I have shown you only for GP and FP. Okay. You can ask the question, how about for arbitrary CTL operators or LTL? Of course, we have not even seen LTL model checking now. We will see that. But, you can say, how about other operators when they are nested ones? Of course, you will have to generate formulas. I've illustrated how you could generate a formula for doing bounded model checking. Bounded model checking means you have to generate for each formula something that, whose unsatisfiability guarantees the absence of counterexamples for up to a bound of k. Of course, you will have to generate the formulas for other temporal logic operators will be more complicated, more more complex in the sense in terms of the size. How you generate them, we will get to that in later exercise in later lectures. But what I've shown you is the key, basic idea by using just G of P and F of P for doing it. Yeah. Okay, now I will discuss the issue of completeness. Okay, so BMC, as we have discussed so far, is incomplete. It only refutes, does not prove. So what are some ways to fix this? Of course, the third bullet is something that I've already shown. You can always fall back to quantifier elimination as with BDDs, and then you can do fixed point calculation as I showed in the first slide. Of course, that is not the idea that you will, you have, the whole idea here was to not use quantifier elimination. So without using quantifier elimination, how can you, do things, okay? One approach, and this was the early approach that was used for, which is actually done by the same guy, Armin Beer, who is credited with inventing this, method using SATs, this Babonian model checking, is to find bounds on the maximal length of counter examples. Okay, these are called completeness thresholds. Exact bounds are very hard to find, and so you can have some upper bounds. That is what I mean by approximations to the maximal length of counter examples. And you will see when I illustrate these the bound of the length of the counter examples are dependent on the property as well as the property in terms of the temporal logic, okay, operators that are used, and certain aspect of it. It is also a function of the transition relation, the structure of the transition relation. But one can come up with certain loose bounds, if not exact bounds, for things. But you should be forewarned that they are dependent on, for property specific, these bounds. So once you compute that bounds, bound for a given transition system and a formula, you can run this for up to that bound. That is one. The other approach is what are called inductive model checking, which we will get to later on, using what are called inductive invariants, and I will introduce that, and they are very much more effective than this completeness threshold methods. Okay, so that is the idea. So I'll introduce define what a completeness threshold is. Okay, so you've seen this. So let's write M turnstile with a suffix K. Okay, phi to mean that phi holds on paths of M, the Kripke structure M, for up to length K. Okay, we say that M in a bounded way, okay, with a bound K satisfies phi. It means that phi holds on all paths of M for up to length K. The idea behind determining completeness threshold is the following. So for finite state models, obviously there must be some D for which, if you checked for counterexamples for up to that length, then it would guarantee that it holds for all lengths. Correct? Because there has to be. I mean, the counter examples, the length of the So because for finite state models, these paths, because they all lasso, at some, counter examples, they all lasso at some point. Therefore, and those lasso sizes length of the lasso is finite. So you should, for finite things, the counterexample eventually has to be finite, and I mean not finite, but finite length lasso. Okay, and that is what. So such a D is what we call as a completeness threshold, and this is due to the fact that all counterexamples have to lasso. Okay, and then for finite state systems, the length of the largest lasso-like shaped counterexample has to be finite. Okay, and that is the reason that there is always a bound on this thing. So, but getting a smallest such D is very hard. Okay. So, for example, for invariant properties like of the kind G of P, what is a very loose bound D? Anyone willing to guess? I'm asking you for G of P like property, that where P is a
Number of states.
Number of states. You're right. Okay, so that is a thing, but that's a very loose bound and not a very useful, useful bound. Okay, for simple liveness properties of a kind FP, you know that it is the length of the largest lasso. Okay, but for more nested temporal logic formulas, it is the exact bound is it can always be expressed, it appears, as some function of these certain parameters about a certain measure metrics of the transition system, as we will see. Okay. Yeah, this is something that I already mentioned. Okay. So I want to, this is something that I've already mentioned, and this is what that we'll be exploiting in this thing. So every for finite state system, not infinite, but every counter example, even infinite counter example, must be of a lasso shaped. So this I've already mentioned. So here is the flow chart for bounded model checking. Okay. Yes. So you unroll the transition function k times, check for, and add some extra formula to that will check the absence of violation to the property for up to that length, and then check if for a counterexample. If an error is found, then you report a bug. If not, you compare k to the completeness threshold, which has to be computed once and for all for a given transition system and a given property. Okay, and then you run it up to that completeness threshold, and you keep increasing k by 1 up to that point. So the more precise the way that you can compute this completeness threshold, the better it will be, the less effort that you will expend in doing this. Yeah, and that is the idea. So now I'm going to describe to you some metrics, define certain metrics on transition systems that in terms of which this completeness threshold will be expressed. Okay. So distance, okay. So length of the shortest path between two states, okay, is what is defined as the distance. That is, see, when you do, yes. So the minimum for between any two states, S and T, the distance between those two states is defined as the shortest path between those two states. Okay, that is one metric that we will, that is what distance is. Of course, if those two are, if a T is not reachable from S, they're not connected, that then the distance is considered to be infinite. So then you have, okay, so there's this parameter which is, which is a metric for a transition system defined as reachable diameter. It's the maximal distance between any two reachable states in the Kripke structure R. Okay. No, what am I saying? The R is the set of all reachable states. Okay, that's what it means. That's what I mean here. So yeah, so among all the states that are that is in the reachable set, okay, between two reachable states, so among all states that are connected, among all pairs of states that are connected, that means there is a path between those two things. The diameter is the maximum among all the distances, okay, between those those two things. Then the initialized diameter is the maximal distance from an initial state to a reachable state. Okay, you see, the reason for defining this distance as the shortest path is because when you do this kind of by doing T star longer and longer paths, and then you're taking the satisfying instances, you're doing pretty much a breadth first search, because if two states are reachable, and that will be caught by by the shortest path. Okay, if something is reachable in k instances, you will get it in that thing, and that's why it is being defined this way. So the minimal distance is what the length of the shortest path is defined as the distance, and these things are the maximal among all states that are connected. Okay, that is reachable diameter. Initialized diameter is one of among all the states that are reachable from any of the initial states. Okay, the maximal distance among all the states that are reachable from R. That is what we define as the initialized diameter. And you will see that the completeness threshold bound can be expressed in terms of these parameters. Okay, so here is an actual example that is illustrated. So these, suppose 0 and 1 are the initial states. And the transition relation is described in terms of edges, okay? So this is, yes. So when you do T S0, S1, S0 consists of 0 and 1. When you do 2 S0, S1, I mean, you will get 2 and 3, okay? Because both of them are at a distance 1 from one of the initial states, okay? So and then there is this 4, okay? So here are states with distance 1 from the initial states, okay? So 3 and 2 have a distance of 1 from the initial state. Why? Because from any one of the initial states, there is a path. The shortest path to reach either 3 or 2 for 3 or 2 is just 1. Okay, although you see there are other paths that that are longer than 1 to reach 3 and 2. For example, the path from 0 to 3 is of length 1, 2, and 3. you know, and 2 is also, to reach 2, there is also a longer path, okay, even from 1. Okay, 1, 3, 4, and 2. But now you must see why the motivation, why we define distance as the shortest path. Because when you do satisfiability check of T S0 S1, or T S0 S1 S0 S1 S2, you will collect all these states, okay, in that one step. In one step, you will collect 2 and 3 because they are the shortest path is how long it, how many unwinding of the T that it takes for you to reach these 2 and 3. Okay, and that's why what the diameter is the longest among all the states that are reachable from one of the initial states. The state that has the longest distance from the longest distance is considered the initial diameter. Okay, so the initial diameter in this case is 2. Why? Because these are the only, these are the reachable part. I mean, the reachable states from the initial, say, 0, 1, or 2, 3, and 4, other than 0, 1, for which the distance is 0. Therefore, the initial diameter here is 4. And of course, the reachable diameter includes even the unreachable parts of the transition system. So you can see that the initial diameter is, you already must have seen that, you must have kind of guessed that the initial diameter is the bound. Okay, that is for you to reach all the states that are ever reachable from the initial states. That's how long the BMC formula by in terms of the number of T's that you have to unwind, the number of times that you have to unwind to will be. Okay, is it clear that the diameter is 4? That's because you see that why is it 4? Yeah, because as you can see, there is the largest distance between any 2 states is 4. 1, 2, 3, 4. Okay. Similarly, there are so that is among the the diameter for the entire transition relation is 4, because it also includes the distances among unreachable states. Okay, so is it clear, the definition of diameter, initialized diameter and reachable diameter? So these are all properties, metrics of a transition system, a given transition system. Once a transition relation is defined, you can get these numbers. Okay, so the completeness threshold for safety properties of the kind G of P is the initialized diameter. Why? What is a witness to the violation of G of P? It is a path from one of the initial states to a state in which not P holds. Okay, correct? So the initial diameter is the largest distance between any initial state, from an initial state to any state that are reachable from the initial state. So if in the worst case, that not P state has to be reachable by a path which is the largest of all the distances between, of all the distances that are of between an initial state and a state that is reachable from force. So in the worst case, that will be the bound. Okay, so yes. Okay, so the diameter for the entire transition system, that can serve as a completeness threshold. There might be other counter examples that are shorter than that, but this is certainly a bound for the entire transition system. Okay, so it's just GP, it's the max K. So if you run up to the diameter, if you somehow you can compute the diameter for the transition system, that can serve as a completeness threshold for these kinds of properties. Okay? The question is, how do you determine the diameter? Okay. Now, that is as hard as the, if not as the model checking problem itself. As you can see, what you'll have to do is, for all, okay, this is what you will have to do. The initialized diameter is the maximum length d of a path leading from an initial state to any state that is reachable from the initial state, such that every path, so there's no other path that is, that takes you to t that is less than d. That is, it is the maximal length of all the paths, maximal length of all the distances for all the states that are reachable from D to any state that is reachable to D. So, which means you will have to do something like this, okay? So, for every path, okay, for every state that is reachable from one of the initial states in distance D, then there will be something that is even shorter than that. It is the maximal. It is the maximal of all those paths, which you can express as a quantified Boolean formula of this kind. This will be like a search. I mean, which is expressed as the non-existence. So you'll have to do this thing for you have to check this query for various Ds, starting from 0, 1, 2, 3, etc., until you reach a D for which this thing that I've shown here, that so for every path that is reachable at D, every other path is so every other path that is reachable from any other initial stage is shorter, is shorter than that. That is the kind of search that you will have to do, which will take, even if you try to eliminate this, you will have to search in a nested way among all the states, and therefore this you trying to find the initial the diameter, or so that even the initial diameter is equivalent to solving this quantified Boolean formula, which is very hard. Therefore, the idea when they were using these things in the initial days was to do some over approximation from looser bounds, okay, which are may be able to get by using SAT solving techniques once for the transition system and for that property. The idea is to solve, if you could express the search for the distance, an upper bound of this distance, as a SAT solving instance, then you solve that once for your transition system and a property, and then you can run your bounded model checking to up to that length. So since computing the initial diameter is very hard, because it requires those solving nested quantified Boolean formulas. There's a looser bound that is easier to compute as a SAT problem. And this one is called reoccurrence diameter, okay? Here between any two states, or initialized reoccurrence diameter when it is applied to states from that are in the initial set. Okay, this one is, what is this? Okay, reoccurrence diameter is the length of the longest path that you can take from any state without any states, the longest you can go from that state, longest path that you can take without any states repeating on that path. Okay, that is, yeah. So how long can you, what is the longest path from that state that you can march to without any state repeating? Okay, yeah, before that lassos. Okay, that is what is called as the reoccurrence diameter. When applied to states in the initial state, in the initial set, it is called initialized reoccurrence diameter. I will show you an example here. Okay. So here you see, for this transition system, 0 is the initial state. So every state, non-initial state, is reachable from 0. Okay, so what is the, yeah, I've already shown you that. So every state is reachable in one step. Therefore, the initialized diameter is 1, correct? Why? Why is the initialized diameter 1?
Any state is reachable from some initial state in one step. So
yeah, that is the shortest distance.
Yeah.
Okay? That's what you'll have to, yeah, that is the shortest. That is the length of the shortest path. Okay, that's what it is. So of course, here you see 1 is reachable in several ways from the initial state. In one step you can do, or you can do, n steps, 2 steps, and so on. Okay, that the shortest distance is what defines the initial diameter among all the shortest. I mean the maximal among all the shortest distance. But here, since every state is reachable from the initial state in a maximal distance of 1, that's why that is the initial diameter. And if you were using bounded model checking, that gives you the exact bound, okay, that you will have to do. But that is, as you said, in general, hard to compute, and that's why we are using some looser bound, which is called a reoccurrence diameter. Sometimes they call it radius. So the reoccurrence diameter is the initial reoccurrence diameter is the longest path from any of the initial states. In this case, there's only one initial state that you can take without actually repeating any of the states, which in this case is the cardinality of the entire set of states, right? Because this is, say, you go from 0, 1, 2, etc., and before you actually loop, okay? That is the longest path that you can take without actually repeating any states. And that's what is the reoccurrence diameter. And the initialized reoccurrence diameter is also an upper bound, okay, on the thing. And we will see that this is easier to compute as and pose and compute as a SAT problem. Before that, I'm claiming here that the initialized reoccurrence diameter for any transition system is indeed an upper bound for the diameter. Why is it so? I introduced the reoccurrence diameter as a loser bound for the diameter. I'm asking you, why is it so?
So when we're looking at normal diameters, we're looking at the shortest path, which is also a like a path with no reoccurring uh, states. So
Yeah, that is kind of the idea. Yes, uh, you're um you're right. Okay, or another formal way to do it is, suppose there is, okay, so R is the reoccurrence diameter. So I think your idea is this is correct, but you can kind of prove by contradiction. Let's suppose that the diameter is D that is greater than R, which is the reoccurrence diameter. So if you do have if D is something that is the diameter, then there must be a path, correct? From some one initial state to some state, okay, which is the which is the shortest path between which is there is a path. If that has is D is greater than that, then you see you can always there must be a repeated state in that. Okay, if they're repeated states, you're exactly that idea is what I use. So you can get a contradiction. So you can remove that repetition and get a shorter one. Okay, and that's why. Yes, you're right. Okay, and a formal way of doing it is you assume that there is a diameter. If the initial diameter is greater than R, then there must be a path between two states, the shortest path in that. And since that D will be greater than R, there must be two repeated states. Then it no longer can be the shortest path. Okay, because once something reoccurs, you can always get rid of that and then get a shorter path. Okay, and that's right. And the key observation that you noted was exactly correct. Yeah. Okay. So so this is easier to express as an instance of a solving. So you have to do this can be computed as the minimal D that makes the following formula valid. Okay. That is, so this formula, what is it saying? For every path of length D D plus 1, okay, that's what this thing. It says that if there is a path of length D of D plus 1, then one of the there must be some of them should have reoccurred. Okay. So you really have to find the longest path before something reoccurs, so which can be expressed as the minimal D that makes this formula valid. So you will have to, it's the minimal D, at which point you will have, if you take a path, if you consider a path of that length, of length D plus 1, then D will be, you have D plus 1, then something must be repeating in that. That's what it's saying. So if D will be the reoccurrence diameter, if for any path that is of length D plus 1, this path is of length D plus 1, if you consider that path, then one of the states on that path must be repeated. Okay, that's what this thing says. This OR is pairwise disjunction of every state that appears in that on that path. So the minimal D that does where this is becomes valid, or the negation of this is unsat. Okay, so you see this is simpler than the other one because there was a nested quantifier here. But even here, how do you compute the minimal D? That requires repeated SAT calls. So you first check this formula for all parts of length 1 and see if it is valid. Okay. If not, then you go to increase D, and then you repose this as a SAT check. Okay, a validity check for parts of length 2, length 3, length 4, and so on. But for each of these iterations, so this is indeed, you have to do it in a loop, okay, where each iteration of the loop involves a SAT check, checking if this is valid, which is checking if the negation of this is unsat. It is still hard, but it is not as bad as the earlier one, okay? Because you know, model checking itself, I mean, that is as hard as model checking. But this is not as hard because it does not have nested you know, quantification, but it does involve repeated SAT invocation. But remember that this thing is not being done for every due in the thing. So you do that once. The bound is done once for your property and for your transition model, and then you can use that for multiple multiple properties. Okay, so that is the idea. So reoccurrence diameter is a loser bound. It is an approximate bound both for safety properties, and it is actually a precise bound for liveness properties. Okay, so you know that is the idea. Okay, so that's how you do. So I go back to this thing. So there is a one-time thing of computing the. If you were to be using this approach, okay, there is what are the tasks involved in there? You have to convert for the yes. So you have to for each property you have to convert that into a what I call as the BMC formula, bounded model checking formula, which for any given k, which is parameterized with respect to the length of the counter example that you eliminate at any one point, that formula, the satisfaction of that formula will be a witness to a counter example. That translation you'll have to do. That is for different properties, okay? And what we saw was how to do that translation for invariant safety property and simple liveness properties. We have not seen for arbitrary CTL or LTM formulas. Once you do that, then you have to compute the bound threshold using this, okay, as once for the transition system. After that, you're in business. You can check any safety property for that transition system by running that loop that I showed you, okay, until up to that completeness threshold. Okay, so that is the idea. That yes, okay. So I'm going to end here and take any questions that you may have.
So for the BDD case, we had like, if we had, so our method was such that we could, check for which state satisfies each of the sub-formulas of a given CTL formula, and then using that knowledge, we could then check for the correctness of the given CTL formula, right? So we could sort of do some sort of a structural induction in CTL formulas. Here is something like that. Is something similar going to be possible?
Yeah, I think the formulas that you generate, the BMC formula, will be generated inductively. You're right. Okay.
Okay.
Correct. Yes, that will be how it will be generated. Okay. So yes. So and there will be a method to generate for each of them, and that will be done inductively for any given length. Yes. Okay, and it will be parameterized with respect to the k. That that is an easy part to follow. I think it is the computing the bound for the bound, an appropriate bound. Okay, so this reoccurrence diameter works for safety property and simple liveness property, but for all nested properties, much harder. Okay, and how do you compute that? Even a loose bound is a matter of, I think there's several papers that have been written on that, And it seems that for a significant class of properties, the completeness threshold reasonably can be expressed as, I think that getting the precise threshold will be hard. Okay, but theoretically it is possible to that people have seen if that can somehow be expressed as a function of the diameter and the recurrence diameter of the transition system for any given formula. Okay, that has been some theoretical goals that people have had, and people have solved that problem, what the tightest bound is for a large class of LTL, LTL formulas. I think it remains open. That is a theoretical problem. Okay, theoretical question of the tightest bound for all LTL formula. I don't think that people have done that, and there are some formulas for which the tightest bound, what exactly it is still an open problem. Okay, but loose bounds people have used, but that is still kind of the problem with this approach. The induction approach, of course, even for safety properties, this one is too loose a bound. Okay, and because it does not, when you do a loose bound, you're not taking the property into account. Okay, because the tight bound will be a function of the property as well as the transition system. The reoccurrence diameter is a loose bound, but then it throws away the property, and that's why it is a loose bound. It's still in for a lot of transition systems that's too big. And the inductive approach is very property directed, at least property directed, and therefore it eliminates having to compute thresholds. Okay, and we will see that. Yeah. So yes, you're right. Okay, I went from one to the other, but yeah. So I hope I have answered your question. Yeah. Any other questions? Any other questions about the assignment? We still have. Yeah. Go ahead. Was there a question?
Yeah, so I had a question about the assignment. Yeah. So once we have like a chain of BDDs from which we want to generate a counterexample, we will have to somehow for each of those BDDs find a state. That is, we'll have to find a satisfying assignment for a given BDD, right? So is there some, like, what is a good way to...
I showed you that, no? Tobin already showed you that.
Yeah, but then, okay, so the all-sat method that he was displaying, that was only available in the Haskell bindings. I could not find a corresponding thing in the C++ binding. I mean, if it is not possible, then I'll have to switch
It's there
languages.
in every library, I think.
Yeah, could you...
I mean, it's there in Python, definitely. I'll just
what is
check.
it? So I searched for all-sat or something like that. And
but I think you should...
It might be called something else.
Why do you want to use all sat? Okay, get all sat. It's enough for you to get one sat. Okay.
Yeah. Even any sat and all I searched, but like okay.
Yeah, but you must actually be looking for any stat. Okay, any one satisfying instance. There must be one. Okay, that there must be there. Okay. If all sat is really basically all of them, they will break. Excuse me.
Kanta, have you done the normal model checking first? Is it over?
No, I mean, no, I've not done it, but I was thinking ahead and I thought of what problems that could have arisen, and this was something that came to mind.
Okay. Yeah, I would do, if you were doing this, I would do one step at a time. Okay? And I'm saying that if there is some help that you need, you should try and do that first. See, I'm taking this, I always take this approach, okay, all these assignments, etc., are learning experiences, okay? So I won't, I don't mind helping you guys out. As long as you put in the effort to do it, okay? And then you hit a roadblock. And then you say, oh, this is the roadblock. How can I solve this? Okay, that's a good approach. I appreciate that. Okay. And then I don't mind help when you do that. Rather than not doing anything, or maybe you do something but you don't know what the roadblock is, and you're not willing to come discuss that in class. Okay, so that is, if is what something that I would not want to see happen. Okay. um, yes, so towards that end, I mean, I would say take step-by-step approach. Define a tau, okay? Just do a repeated tau, starting from false, which is, something that you'll have to do. Then you put in that one loop, okay? So see what the issues that you face are. So first, there is a tau that you have to define. I mean, if you're able to
I
define,
pasted the link to the OneSat and AllSat, how
okay.
you can implement them using the C library in the chat. So Digonto, if you look in the chat, you will get a link.
Yeah, there is one that is posted.
Yeah, thanks. I am looking at that.
Yeah, so it is getting late today, so I want to stop here. So if you can, by next Monday, have worked out all the, at least made an initial attempt, and if you list out all the technical implementation issues that you're having, I don't mind discussing that, and even giving some partial solutions as we move along.
Actually, sir, actually, I have implemented everything up to normal model checking without fairness.
Without fairness.
By
Okay.
using the star and fixed point, everything.
Working?
I just wanted some test cases
Examples.
to test my code.
But why don't you use in the, before we get you something, I mean, I can get you some toy examples, plenty of them, and but use that example, the microwave example. It's already there in that was discussed in the class and in the book. The other example that I would use is, for certainly the mutex example. I mean, the three examples, the microwave example, I mean, I've given you a lot of toy examples that I've also shown you in the slide.
Microwave example is a bit harder to encode up. The transition relation would be very complex.
Oh, I mean, what? I mean, it has, no, I mean, it has 4 states or something like that. So why would it be hard? You're just defining the transition relation. So it's a Boolean function of 4 variables. I think there are only 4 variables there, 4 or 6 variables maybe. It's even a synchronous system. So all you have to do is you have to give one function for each of the bits. So you will have 6 functions that have to be defined as Boolean function. I don't think it is complicated.
I'll see.
That is not complicated. Now, I know that actually the mutex example might be a little bit more complicated. Actually, even that is not that complicated because it has the PC there, and therefore that might make it a little bit more complicated. But and even there, because so many of the states are unreachable, you can just your transition relation will be fairly compact. You will see, surprisingly compact. Yeah, those are the states. Certainly, microwave example I would use. Okay, and if you want to start with even smaller one for your check, use those toy examples that I used in the thing to illustrate CTL and LTL. Yeah, those are very toyish. They only have 5-6 states. Yeah, not even, yeah, only 4 states or something like that. Try it out, I think. Okay, so I'm going to end here, okay, since it's getting late. So I urge everyone, people who are here, people who are out there, who might listen, and you may want to pass it on, to do all the things, okay? Even if you can't complete it, do all the things. See what the gating factors are. Any implementation issues that you have. You're stuck either because you are run out of ideas or you're having implementation issues. Bring it up, and I'm willing to discuss, okay? Yeah. And yes. So by the way, the next project, which will be, I'm thinking of, doing it in pairs, will be an implementation of a SAT model checker of not for the CTL and so on, but rather for one of the inductive techniques for which I will be describing the algorithm in class. Yeah. Okay. I'm giving you a teaser as to what it will be. So you might want to think of getting some teammate for your thing, doing it. That will be done using SAT. Okay, I'm gonna stop sharing.
But sir, it would be very convenient if you provide the test cases. Would you be providing, sir?
Yeah, by test cases, is it enough if I showed you the I mean, obviously I've given you the list of examples, but you want it coded up as transition systems, as formulas?
Yeah, yeah, as a formula.
That I can do. Yeah.
Okay.
Yeah, that will do. Yeah. Okay.